This video is on intercepts of quadratic functions. So let's start with some definitions. An x-intercept of a function, of any function, is a point where the function intersects the x-axis. That intersection could involve crossing, or it could involve just touching the x-axis and turning around and heading back the same way. But as long as it intersects the x-axis, that's an x-intercept. And since the y-coordinate of any x-intercept is 0, we frequently refer to the point just by its x-coordinate. This is sort of a shorthand because an x-intercept is technically a point and has 2 coordinates, but this has just become the way to refer to it, and we will follow that convention. A y-intercept of a function is a point where the function intersects the y-axis. Now, the one way that this is different from an x-intercept is a y-intercept cannot bounce and return, because if it did that, something like this would not pass the vertical line test. So, it wouldn't be a function. Anyway, since the x-coordinate of any y-intercept is 0, we frequently refer to this point just by its y-coordinate. Alright, intercepts of quadratic functions in particular. Every quadratic function will have exactly one y-intercept. You can always find the y-intercept by setting x equal to 0 and finding y. And a quadratic function might have 0, 1, or 2 x-intercepts. And you can always find the x-intercepts, however many there are, by setting y equal to 0 and solving for x. So let's have an example. If I wanted to find the x and y-intercepts of the function y equals x squared minus 8x plus 15, to find the y-intercept, you use x equals 0 and find y. So I take my function, I substitute in 0 for x, and y, it's 15. And then to find the x-intercepts, that should be plural, x-intercepts, because this function actually does have more than one. I'm going to use y equals 0 and find x. So I start with my function. I substitute 0 for y, and now this next step is really unnecessary, but I find that most students are more comfortable with the major business of the equation on the left, which is fine. Then there are several ways that we can solve this, but notice that this factors quite nicely, and if a quadratic function factors, and you can see easily how it factors, then that is definitely the easiest way to solve this. This factors as x minus 3 times x minus 5. And notice that I've got the x minus 3 times x minus 5 equals 0. So I can use a special property of 0, since I have something times something equal to 0. Then one or the other has to be 0. That's the only way that this can happen. So if I'm looking for all of the solutions, I'm going to set each piece equal to 0. So x minus 3 equals 0 will give me one solution, and x minus 5 equals 0 gives me another solution. And x minus 3 equals 0 will give me the solution of x equals 3, x minus 5 equals 0 gives me the solution of x equals 5, and so these are the 2 x-intercepts for this function. So sometimes a function's just not going to factor that nicely. If it does not factor that nicely, then you can use the quadratic formula. Well, you can use the quadratic formula in any case, but if it does factor, it's just easier to do that. Remember, this is the quadratic formula. This is sort of prerequisite knowledge, but a quick review. In order to use the quadratic formula, your function needs to be in standard form of y equals ax squared plus bx plus c. Actually, you're setting that equal to 0, so what you have is ax squared plus bx plus c equals 0. That's where the a, b, and c come from. So, our example here, if I want to find the x-intercepts of y equals x squared minus 8x plus 13, changing that from 15 to 13 means that now it's just not going to factor. So I can know that I am trying to solve this equation. I set the y equal to 0 and try to solve this. So by using the quadratic formula, I get negative b plus or minus b squared minus 4ac all over 2a. Simplifying this gives me 8 plus or minus the square root of 12 over 2, and simplifying that gives me 4 plus or minus the square root of 3. Well, the one step that I did skip here, since 12 has a factor of a perfect square, which is 4, 12 is 4 times 3, you can rewrite this as the square root of 4 times the square root of 3, and of course the square root of 4 is 2, and then I divided by that 2, leaving me with this. Alright, the principle of square roots. It's a very useful principle. When finding x-intercepts for a quadratic function that is given in vertex form, we can use the principle of square roots. The principle of square roots is just that rule that lets us say, if I'm given the equation x squared equals a number, then x is equal to plus or minus the square root of that number. So if I'm given x squared equals 36, x equals plus or minus 6. Now, let's look at that. So I've got something in vertex form. Notice that vertex form will always have a perfect square. In this case, my perfect square is x minus 7 squared. So I'm setting that equal to 0. The y is equal to 0. I want to isolate the perfect square. I want to get the perfect square on one side by itself. So if I move that 12 over and then divide by 3, I will have x minus 7 in parentheses squared equals 4. So I have a perfect square now equal to a number. And so that, when I apply the principle of square roots, gives me the thing that was being squared equal to plus or minus the square root of 4. In this case, square root of 4 4 is a perfect square, so there is an integer square root, and if I add 7 to both sides, I get x equals 7 plus or minus 2. Now, if this were an irrational number, I could leave it. If it had been something like 7 plus or minus the square root of 5, I would just leave it as it was. But since it is an integer, I can give my answer as 2 separate integers, 7 plus 2 and 7 minus 2. So the two x-intercepts are 9 and 5, from 7 plus 2 and 7 minus 2. And that concludes our video on finding intercepts for quadratic functions.